So, hello friends, in this tutorial we are going to explore about the multiphase solver, that is the interFoam. Okay, so starting from brief idea about the multiphase solver. First I will introduce that what is a multiphase solver and what is a numerical model approach generally used to solve the multiphase problems. Okay, so starting from the brief overview, we are going to see test case, then we are going to explain about the some basic idea about the interFoam, and finally after explaining the test case and the basic interFoam idea, then we are going to explore the coding aspect of the interFoam. Okay, so I think in this tutorial we are going to just explain about the basics of the multiphase solver and then the one tutorial of the interFoam. In next tutorial I will explain about the some basic concept about the coding aspect level of the interFoam. Okay, so let's start. So what are the base multiphase solvers? So multiphase solver, when we have to solve more than one phases problem, then it is classified into the multiphase solvers. Okay, so for example, if you want to characterize the multiphase flow problems, so we can characterize in two ways. Okay, so first we can see that we can characterize it as what are the physical component present in a flow. That way we can classify it into the these forms, like gas liquid flow, gas solid flow, liquid solid flow, and liquid liquid and three phase flow. Okay, so this way you can classify the multi-phase flow problem. And second one is the multi-phase problem that is classified into the separated form, mixed form, and dispersed flow form. Okay, okay, so speaking of separated, suppose if you have a one glass of water and if you are pouring some oil into the glass, then the oil phase is completely separated from the you can say the water. Okay, so that kind of the flow is known as the separated flow. So where the both the different phases can be separated easily, that you can see that as a separated kind of the multiphase problem. Next, you can say that you have a one bottle of water and you are pouring some food color. Okay, so color food, if you are mixing, then you know that the color food is going to mix in the water. Then that kind of the flow we can see as the mixed kind of the multiphase flow problem. Now third one is the dispersed flow. So in this dispersed flow, suppose that bottle of the oil and water you are shaking very long time bottle, and after some times this droplets of oil is going to mix into the water, and it will create some small bubble particles, or you can say the small dispersed oil particles inside the water, and that kind of the flow is known as the dispersed flow. Okay, so this is the three kind of the multi-phase flow problems you can classify it in this way. Now there are generally two approaches used to model the means multi-phase flow problem, that is the Eulerian approach and Lagrangian approach. Now I can give you some simpler example to give you illustrate about the Eulerian and Lagrangian. So suppose you are sitting in a park and it is raining there, and you are when you are observing a particular location or a particular volume or particular given position, and you are observing the how the droplets of air is falling down, then that location, when you are considering that type of approach, is known as the Eulerian approach. Okay, so you can see that this is the control volume approach. So here it is a control volume is given, or you can see that the one particular location is given, then it is known as the Eulerian kind of approach. Okay, whereas the Lagrangian approach, we are considering, suppose you are holding some drop of water on your hand, and when the water droplets falling down on your hand, and the flow of water droplets, how the water droplets is flowing over your hand. So the in this approach you are considering a particular water droplet, or you can say that you are considering a particle. That kind of approach is known as the Lagrangian approach. Okay, so here we are not considering a value, here we are considering a particular particle. So that is why the Lagrangian approach is called as the particle approach. So speaking of Euler approach, in this approach we are first assume that the both phases are completely mixed, and what we do here, we solve each equations for a different phases, and then using some concept of the some other correlation, we interlink between the different phases. Okay. So for example, if you are solving the energy equation for different phases, then we solve the energy equation for different phases. Okay, when we solve the different equations for the different phases, now we want to connect between the phases, then we also solve a energy transfer equation between the two given phases. Okay, similarly if you solve for the mass transfer, then we will solve a separate equation for the mass, and then to connect between these two phases or different phases, we solve the mass conservation. And we talk about the, if we talk about the Navier-Stokes equation, so for different phases we are going to solve a different Navier-Stokes equations, and to connect between these two phases or different phases, we will solve the drag forces. Okay, so this way we will solve this Euler approach. In Euler-Lagrangian approach, we are going to solve when the dispersed phase. Okay, so the dispersed phase has a significant number of the particles. Okay, so for example, if you are solving a bubbles droplets inside a flow, then the number of bubbles has a significant number. Okay, that way we have to solve the Eulerian-Lagrangian approach. Okay, so the last one is the VOF model, which is our primary interest of this tutorial. So remember that the interFoam is the best on the VOF model. Okay, now this is suitable when the interface between the phases is a primary interest. Okay, so when your whole focus is the interface between the two phases, in such cases where we generally use the VOF model. Okay, so let's explore about the VOF model and the tutorial case. So this is the idea about the VOF model. So whenever the interface between the different forces is can be tracked, okay, in such cases VOF model is very suitable. Okay, now in VOF model we solve on a given mesh. Okay, so the mesh grid is fixed, it is not going to change. Only the interface, this function C, is going to be changed based on the whatever the equations we are going to solve. Okay, and what is this interface or fraction function? So fraction function indicate the presence of a given phase. Okay, so for example, I am talking about a single phase, that is, suppose you can take as the water. Okay, now if we have a given a phase, now this C function is going to tell you that whether this, what is the amount of water is present or what is the amount of water is not present. Okay, so generally there are three conditions of the C. First, where the water is completely present. Okay, so suppose we are solving air bubbles inside a given water. Okay, so water is going there and there is one air bubble. Okay, now if C is equal to 1, then it means that the water is completely present here. Okay, there is no air is present, only water is present here. That is the C equal to 1. And if air is present, water is not present, in such situation we are going to keep C is equal to 0. Okay, now if the interface between the water, if the water droplet is present, then there should be interface. Okay, so the transition from the water to air or air to water is called as the interface phases. Okay, now the value between the 0 to 1 is known as the presence of the interface, means that there is transition between the water to air or air to water is taking place. So this is the C function which is going to decide that whether the this is the phase 1 or phase 2. That is the whole idea about the VOF model. Okay, now let's see one test case or one tutorial, and then after that we are going to see the mathematical equation or governing equation and how this formulation has been done in the OpenFOAM. Okay, here I am in the terminal of Ubuntu. Okay, so you can see that this is the folder structure of the OpenFOAM 6. Here I will go to the application part and here I will go to the tutorial folder. Okay, in tutorial folder I will go to the multiphase solver. Okay, so this is the multiphase folder. Inside the multiphase folder I will go to the interFoam. and there are different cases you can see are that. Now here the laminar cases I am taking. Now I am copying the dam break case. Okay, so either I can copy here or I can use the terminal. Okay, so I will open the terminal and let me zoom in little bit. Okay, so I can use the cp minus r, and of course first I have to create the OpenFOAM 6 environment. So now cp minus r, and then I will type the foam src. So you foam tutorial, and in foam tutorial I will go to the incompressible. Okay, sorry, I have to go to the multiphase solver, not incompressible. So after tutorial I will go to the multiphase, and in multiphase you can remember phase we have to go to the interFoam. Okay, in interFoam you will remember that I will go to the laminar. In laminar I will go to the dam break. Okay, now I want to copy this whatever the folder structure is here to the current position. So in Linux this is the symbol for the current position. So we have a copy here. You can see here that the folder dam break is already given here. Okay, so this is the case of the dam break, and I can go to the dam break even. Okay, so this is the folder structure of the dam break. So we have zero folder, constant folder, and system folder. If I open this folder, that is the dam break. So you can see here that there are different folder structures provided. That is the alpha water, PRGH and URGH. Okay. Now if I open this all run folder, okay, so you can see that different command has been written in the all run. Okay. So first it is going to run the block mesh, then set fields, then application. Okay. So block mesh is going to create a mesh. Okay, so whatever the mesh condition is provided in the block mesh, that is going to create it. So we can run by seeing this command line. We can run the block mesh here. Okay, so first we are going to run the block mesh. Okay, so now our mesh has been created. Okay, so we can even see the mesh here. So we can see the mesh here. So this is the meshing that we have created using the block mesh. Okay, so it has been created using the block mesh. This is the meshing. Okay, now next command you can see here that when you open the all run, you can see that after the block mesh you have the set field. What is the set field? So set field is the one folder you will find in the system folder. Okay, so you can see here that let me open in the Genie folder. So that is the set field. Okay, now what is it is going to do? It is going to read the create one alpha.water folder. Okay, so what it is going to do? It will first create the value of the alpha.water equal to 0. So this is the first job, that the default value of the all the value scalar field, which is the name of the alpha.water, and it is going to assign the every cell is equal to 0. This is the first job. When we are going to run the set field command, it is going to give a default value of 0 of this value scalar field. Okay, so this is the first job. Okay, and then after that it is going to find the all the cells in this given box. Okay, so whatever the cells is given in this box, it is going to assign this 0 value equal to 1. Okay, now this 0 value, all the all the cells in this box is going to change into the 1. Okay, so what I mean to say that, let me first show you. Okay, so first I have to remove this .org. If you want to use this folder, then this .org must be removed here. Okay, so this is the alpha.water. Okay, so remember you see that this is value 0, this is 0 equivalent. So patch at the patch there is no cells, so there is a generally we provide the zero gradient or the inlet outlet. Okay, so what is the inlet outlet boundary condition? In a little moment I am going to explain you. But so you can see the different field that is present in the zero folder. So you can correlate here. This is the field present here. This is also field present here, and this is also field present here. So you can find there this all the three volume scalar field is seen here. So this is the U field and this is the U field. Okay. So you can see here that every field will be cell on a given. So every cell has a zero value. Okay. Because the boundary condition we are providing here is 0. So all the internal field is going to the 0 value. That is why this every cells has a 0 value. Now this set value is required here if you want to change the volume of a specific cells. Okay. So that is why we are going to use this volume set field command. Okay. So what this set field is going to do, we are going to change the value equal to 1. Okay, so let me put here some value, then you will relate and later we will change here. Okay, so now what we are going to do, we are going to change the volume scalar field of alpha dot water equal to 0.5. So this default value of 0.5, this default value of 0 is going to change into 0.5 and only in specific cells, that is this cell, this is the boundary condition of the given box. Whatever the cells is given in this box, that is going to assign a value of 1. Okay, so now let me run the command the set field. Okay, so setting internal value of the volume scalar field, and now the cells within the box is assigned a given value. Now let me open in the paraFoam. Now if I open the alpha.water, okay, so you can see here that you can compare from this given value. Okay, so you can see that everywhere other than this value, everywhere the value is 0.5. Okay, so this is the condition that everywhere the value should be 0.5, but within a box the value should be 1. Okay, so you can see here that within the box, this is the given box, the value is equal to 1, and other than this box, everywhere the cell has the 0.5 value. Okay, now let it do as earlier. So we need a 0 if water is not present. So wherever the alpha that water is given, there is no water, and wherever the alpha that water equal to 1, there is a water is present. Okay, so let's see after running this. Now if I open the case into the paraFoam, so okay, you can see here that, so this complete one is the where the water is not present, and suppose maybe we are considering the air. So here it is not going to first solve the governing equation. Okay, because the alpha dot water is equal to 0, but this is the water is filled here. Okay, now you can see that there is a transition between the water and the non-water zone. So this is the non-water zone and this is the water zone, and this is the interface that we are talking about. So here the value is lies between the 0 to 1, and here the value is 1, and here the value is 0. Okay, so now the water is going to splash out from here, and it is going to hit the dam. This is a dam present here, and we are going to see that what is the effect of the on the interface of the water when it is going to hit the dam. So this is the problem, and this is the how the interFoams see what are the different phases available here. Okay, so here you can see here that the value is 1 if water is present, and here it is the non-water zone. Okay, for running, let's see that what is the control dict. Okay, so control dict, it will start from the here 0, and it is going to end in the 1 second, and the delta t is the 0.001. Okay, so this is the condition of the given in the control dict. Okay, now I can run interFoam. So it is running, and let's see the different boundary condition present here. Okay, so in zero folder, this is the condition that where the water is present and where is the water is not present. And if there will be different other phases like air is present, then this will be alpha dot air. If there are other phases with oil will be present, then this will be alpha dot water. And this is the PRGS because interFoam solves on the P plus RGS pressure field. Okay, so it also consider the gravity. That is why it is the PRGS it is going to solve. Okay, so this is the different condition you can see there. This is the fixed flux pressure condition is provided for the pressure gradient. Okay, and it is solving in the 2D case. Okay, so that is why this one is taken as the empty type of boundary condition. This is the velocity. Okay, so left ward and different walls has the no slip condition, and only the water means at first sphere has the pressure inlet outlet velocity is given. Okay, so it means that generally the whatever the flow is given here is it is deriving by the gravity here. Okay, so now we can see the simulation result here. So this is the U, and it will fill. This is the going to condition here. So let me show you. So this is how the different U field is seen here. U field can be seen here. Now the most important part is the alpha. Okay, so you can see that how this alpha is striking with the dam. Due to the gravity, it is falling down. Sorry. Due to gravity, it is falling down, and then it is striking with the dam here. Then water will splash out. Okay, so you can see now you can see that it is every time it is also capturing the interface here. Okay, so you can see that these are the number of cells. Okay, so this 1 2 3 here the value of the interface is given here. Okay, so here in every cells the value of alpha is equal to 0 or 1, but this cells 1 2 3 1 2 3, or you can also consider this cells. This number of cells are going to the alpha equal to either less than 1 or greater than 0. Okay, but this cells having the alpha equal to 0 or 1. Okay, so that is how this interFoam works. interFoam only consider the concept of that is the fraction function, and based on the fraction function it is going to tell that which kind of the phase is available in a given cell. Okay, so remember I also told you that this mesh cells number of cells or mesh is going to be fixed grid. So you can see that the grid is fixed, but still the water is splashing out because of the given fraction function. Okay, so this is how interFoam has been solved in the open form. Okay, so you can see that how this different condition is changing here. Okay, so I hope this tutorial is helpful for you. So please subscribe my YouTube channel, and also please share these videos to your friends, because more number of views and more number of likes motivates me to create more kind of information for you and more kind of video tutorials for you. So thank you for watching videos. Thanks to all for watching.